Okay, so today we're going to be talking about continuity and differentiability, and we'll start with continuity. Continuity, as the name implies, just means is a function continuous, and for a function to be continuous at a point where x equals c, it has to meet three conditions. So first, the limit as x approaches c from the left side, that's what this negative means, of the function has to be equal to the limit as x approaches c from the right side of that function. And the second condition is f of c exists, right? And the third condition is f of c equals the limit as x approaches c of the function. So let's look at an example. I'll just draw a clearly continuous function right here. We'll call this f of x, and we're checking if it's continuous at this point here. We'll call it c because that's what we did up here. So first, the limit as x approaches c from the left has to be equal to the limit as x approaches c on the right. And we can see on this graph, as the function comes from the left, it comes to the same point as it does as it comes from the right. And so that means it meets this condition, where the limit from the left equals the limit from the right. Second off, f of c has to exist. And we might think that this condition takes care of that, but not necessarily, because we could have something like this, where we have a hole here. And we'll talk about that when we get to discontinuities. So we have to check if f of c exists at that point, or in other words, if the function has a value for that given x value. And we see it does, because at x equals c, there is a point on this line that exists. And thirdly, we have where the function value has to equal the limit. And one place where it wouldn't is if we had not necessarily a hole, but something like this, where the function is steady and then jumps to a point and then goes back. So this would be a discontinuity, because the function value at this point does not equal the limit as it gets close to that point. So for it to be continuous at x equals c, this has to be a point that exists on the line and is equal to the limit from both sides of it. And quickly, you don't really have to remember all these. You just have to check at x equals c, does the limit equal the function value? That's what we always say. It's continuous if the limit from both sides is equal to the function value at that point. And that's what makes a function continuous. And to be discontinuous, there are three ways that can happen. So we'll go over the types of discontinuities. Right? So the first one is called a hole, where if we had, say, something like f of x equals squared minus x minus 6 over x minus 3. Now you may notice that for this numerator, x minus 3 is a factor. It would be x minus 3 x plus 2 over x minus 3. And you may think to cancel these out and be left with x plus 2. Now on the graph of this function, it would look like x plus 2, since these would cancel out. So you have x plus 2, which would be this, but this is not the original function if you cancel these two out and are just left with x plus 2. So we can't just graph this and say, okay, that's our function, because our function does have this denominator right here. And if you notice, when x equals 3, this denominator is going to be equal to 0, which means at x equals 3, we have what's called a hole. And that means that there is no function value when x equals 3, which also implies that this function is discontinuous at x equals 3, because the limit doesn't equal the function value, because there's no function value to it be equal to. So that would be a hole. And the second type of discontinuity we'll look at is called a jump discontinuity. Jump. Now this only happens with piecewise functions. Remember when we had like f of x equals and then something like this, where it'd be like x plus 2 if x is less than 1, and then if it's, we'll say, negative 2x if x is greater than or equal to 1. So if we graph this, we would have this function, like this line, everywhere until we get to 1. Right? And then there'd be an empty dot here, since this is less than, not less than or equal to. And then it jumps down to negative 2. Jumps down to negative 2 when x equals 1, because it switches to this function. So that's why we have an open dot here, so we can have a closed dot here, and then it would look something like that. So that's why it's a jump discontinuity, because as you can see, it jumps from here to down here, which like breaks the function, making it discontinuous. And the third one, the third discontinuity we'll look at is called an asymptotic discontinuity. And if you notice the word asymptote in there, that's because the function is discontinuous due to an asymptote. So if we have f of x equals, we'll do 1 over x minus 1. If we graph this, we see that at 1, there's an asymptote, because this denominator can't be equal to 0, right? Because if we plug in 1, that would be 1 minus 1, and that's 0. So we have an asymptote here, where the graph does something like this. Right? No. It would be it would be like this. So that's what our function does at x equals 1. It switches from negative, like approaching negative infinity, to approaching infinity because of the presence of this asymptote here. So that's our last type of discontinuity, is asymptotic. And now we'll get into some examples of questions you might be asked. So to review the 3 types of discontinuities they have are whole, where that's just a function that doesn't have a specific value at like a specific point, where like we said we had like the line, but there was like one point here that didn't exist. So that was our whole. And we have a jump, where we have a function that goes like this and then jumps up here or something like that, where there's no connection between the two functions. And then the third one was due to an asymptote. And that was like if we had an asymptote here, because there's no function value at that point. All right, so if we look at some examples, I already went through the first one with the whole, where we kind of factored the numerator and canceled, but we had to leave a hole at that point. Another one is Alright, so if you're asked to find a value of k to make some function continuous, and you're given let's see, x plus 3 for x is less than or equal to 2, and kx plus 6 for x is greater than 2. And like always, I'd encourage you to try this on your own before I go over it. So the way to do this is, for this function to be continuous, it needs to connect at the same point. Like this function and this have to come together at the same, like, f of x value for x equals 2. And so the way that we solve this is by setting these equal to each other. So because that's the way they come together. For them to come together at x equals 2, they need to be equal to each other at that point. So we set x plus 3 equal to kx plus 6, and we're only worrying about where x equals 2, since we know these functions are both continuous everywhere else. We're just trying to get them to come together at the same point. So we can just plug in 2 for x. So we get 5 equals 2x plus 6. And then we can just, 2k. Since we plugged in 2 for all the x's. And now we can just solve for k. So we can say 2k equals -1 by subtracting the 6, and then k equals -1/2. So what this means is, by putting k in for -1/2, that makes this piecewise function continuous everywhere. And if we graphed it, it would look something like this. It would look like, so if we say this is our 2, and our x plus 3 would look like this, and then this function here, I meant to do, my bad, I meant to do greater than or equal to 2, and then less than 2 here. And so that would be like that. So we were just trying to find the slope of this line to make it connect at this point. Alright, and another example I like is find this is going to be another piecewise function. So it's find all values of c to make the function continuous everywhere. And you're given x equals, it was 1 minus x squared for all x is less than or equal to c, and then x for all x is greater than c. So we need to find where to connect these two functions to where they're equal to each other. Because right now, if we graph these two separately, here we go. If we graph these two separately, that won't work. We have something like this. And that's our 1 minus x squared. And then we also have this, right, 1 minus x squared. Well, we also have this y equals x up here. So we need to choose where to stop this function on the, or this function on the left, and connect it with this function on the right. So, because as you know, this whatever this value of c is gonna like stop this function from existing further and switch over to this function. So if we put c here, that would stop this line from existing prior to c and stop this from existing after that point. And that's going to be one of our solutions, because we're finding where to stop this hyperbola or parabola to get it to connect with the line. And if you saw before, I'll redraw this. Another solution would be right here, because if we stop the parabola, here, and then continue with the line, that would again make this function continuous. So we have to again set these equal to each other. And so we have to set 1 minus x squared equal to x. And then all we have to do for this one is just solve for x. And then that'll give you the points of x, where if you plugged in to x, they would be equal to each other. Right, so we get negative x squared minus x plus 1 equals 0. And it may look like you can factor this, but we're going to have to use the quadratic equation for this, since you can't find any numbers that multiply to -1 and add to 1 after you pull this out. So we're going to have to use, if you remember, it would be negative b plus or minus root b squared minus 4ac over 2a. And that's what x equals. So if a equals -1, because that's the coefficient for x squared, b equals -1, that's the coefficient for x, and then c equals 1, we can plug these into here. So we have 1 plus or minus, because that's negative b, square root of b squared, which is going to be 1, minus 4 times -1 times 1. Whole thing over -2. And this is going to be equal to 1 plus or minus the square root of 5, after we make that positive, over -2. And that's what x equals. 1 plus or minus square root 5 over -2. And that's actually going to be our answer. So if c is 1 plus square root of 5 over -2, that would be a solution to make this function continuous. Or if it was 1 minus square root of 5 over -2, that would also make it continuous. So that's how you solve that one. And that's actually really close to the golden ratio if you care about that. Right. And now we can start talking about differentiability. So differentiability just means, is a function differentiable, or can you take the derivative at that point? And if you remember, we'll do a quick review about some derivative stuff. So say you had this function, right? If you had This is our f of x. I'll label these points A, B, and C. So if we said, where is f prime of x, if we asked if it is, when is it 0, when is it positive, and when is it negative? We should be able to say f prime of x, or the derivative of f of x, is going to be 0 at A and B, because that's where the tangent line has a 0 slope. When is it positive? That means when is the tangent line has a positive slope, and that would be from B to C. Anywhere in here, that's when the derivative would have a positive slope. And negative, you should say, also from 0 to A, because you're going up here as well. And it's negative anywhere from A to B, because that's when this function is like going downwards and the tangent line has a negative slope. So just a quick recap of how a derivative works. So the ways, it's best to explain this on the ways where it is not differentiable, and there are 4. So if the if f of x has a sharp turn, a discontinuity, a vertical tangent, or a cusp. So if a function has any of these 4 at a given point, that means it is not differentiable at that point. And I'll go through each of these. These 2 are kind of the same, sharp turn and cusp. So for a sharp turn, if we look at, we'll do like an absolute value function. Alright, and we'll call this C. That's what we've been doing. So if we say f of x equals the absolute value of x minus c, that'd be this function here. This function is not differentiable at x equals c. It is differentiable everywhere except x equals c because of this sharp turn it has right there. Okay. So that would make this function differentiable everywhere except from where x equals c because of that sharp turn there. And for discontinuity, that's why we need to learn where a function is continuous, because if it is not continuous, it's not differentiable. So if you think about it, if a function is differentiable at a point, that means it's continuous at that point. But if it's continuous at a point, that doesn't necessarily mean it's differentiable. Like we just saw, it was continuous at that point where it had a sharp turn, but you can't take it's not differentiable at that point. So there's what we say is differentiability implies continuity, but continuity doesn't imply differentiability, because that just says if something's differentiable, it's continuous, but if it's continuous, it's not necessarily differentiable. So moving on to the third one, if it has a vertical tangent, and we call these points of inflection, once we get to doing like second derivative tests and everything, we can do more with points of inflection, but that is when a function goes like here, I'll do, yeah, okay. I'll do like here for f of x equals the cubed root of x, right? You can see that this function at x equals 0, it has like a vertical tangency. That means it goes like straight up. Right here at x equals 0, that means it's not differentiable. Right? Because if you think about it, the slope of the line tangent to that point is vertical, and if the slope is vertical, that means, well, slope like means derivative, so the derivative at that point has a undefined slope, so that means that it is undefined, like the derivative is undefined at that point, which means it's not differentiable. So we've covered if it has a sharp turn, it's not differentiable. If it's discontinuous, it's not differentiable. And if it's a vertical tangent, it's also not differentiable. Right, and the last one is a cusp. Again, kind of the same as a sharp turn, where if we had, I'll say, like this, where f of x equals the cubed root of x squared. This has a cusp here. Again, it's a sharp turn where it's continuous but not differentiable. Right? And those are our four times where our function is not differentiable. Right? And that's really all I have to go over for continuity and differentiability, because it's not a big concept. It's just whether or not you understand, okay, is it continuous? That's when you need to think about, is the limit equal to function value? So is the function value at a given point the same as what the function approaches from the left and right side of that? And then differentiability is if it doesn't have a sharp turn, a vertical tangency, or discontinuity. So yeah, these are kind of pretty easy stuff, and probably one of the easiest things you'll have to do this year. But they are important to be able to understand. All right? Any questions? Leave them in the comments. I'll do my best to answer. All right. Next time we can start probably with the intermediate value theorem, and that talks about how a function must act given starting and end points. Yeah, we can get into that next time.